Welcome back to another video in this series where I'm summarizing and providing code examples for the popular book Reinforcement Learning by Richard Sutton and Andrew Barto. In the previous video, I showed how the full reinforcement learning problem can be defined as a full Markov decision process. And in this video, we'll learn about our first set of solutions, which are called dynamic programming solutions. Dynamic programming refers to a collection of algorithms that can be used to compute policies to solve an MDP given a perfect model of the environment. Specifically, a perfect model of the environment means that the transition probabilities, or the likelihood of ending up in a given state when taking an action from another state, as well as the reward model, or the likelihood of getting a particular reward for being in a particular state, are known for the entire environment. Dynamic programming methods are often limited in practice for two reasons. Firstly, they assume a perfect model of the environment that's often unavailable for most problems. And secondly, they're very computationally expensive. They are still, however, useful because they serve as a theoretical foundation on which most advanced reinforcement learning methods are based off of. Most advanced RL methods can be thought of as attempts to achieve the same effect as DP, just with less computation and without the assumption of a perfect model. The key idea behind DP is the use of value functions to organize and structure the search for good policies. DP will be used to compute V star and or Q star, and once we have these optimal value functions, deriving an optimal policy is trivial. DP algos are obtained by turning the previously shown Bellman equations that I saw in the previous video into update rules for improving approximations of the desired functions. So consider the case where you have some policy pi. How could we evaluate this policy? One way would be to get the state value function, v pi, for this policy, which would tell us how valuable this policy thinks that each state is. So this process is called iterative policy evaluation, or prediction. And the intuition behind this policy evaluation algorithm is that you start with some random state value function, v0, and you iteratively update the expected value of each of the states under v0 using the previously shown Bellman equations while following the policy that we're trying to evaluate. So every time we update all of the state values, we consider that a new version of the value function, so v1, v2, v3, etc. And as we keep changing the value function, it will eventually converge to v pi and be an accurate estimate of how pi values each of the states. Since we are updating our value function iteratively until it reaches v pi, this is called iterative policy evaluation. The algo is shown here. The updates done to the value function are called expected updates because they're based on the expected rewards the agent will receive. So in other words, the agent never actually steps through the environment, but rather uses its perfect model of the environment to estimate what rewards it will receive. And IPE can be done with two separate arrays or in place on one array as shown in the pseudocode here. The algo runs until the state values stop changing under a threshold theta, and under this threshold, the algo has approximated v pi. The main reason for computing the value function v pi for a policy is to help find better policies. Once we know the value function for a policy, how can we improve on it? Right? Consider the case of an agent being in some state S and having access to some policy pi and its state value function v pi. Pi already tells the agent which action to select, but could one of the other actions be better? One way to verify if one of the other actions is better is to choose some other action that pi would not choose, and then afterwards continue to follow pi. And if this leads to a greater expected value than the current expected value for the state, which is v pi of s, then this implies that this other action is actually better than pi's recommended action. In other words, changing the policy to select this other action would mark an improvement to the policy, and this is called the policy improvement theorem. We can encapsulate the value of selecting any action A from state S as Q pi SA. The algorithm can be understood as looking at all the other states the agent could end up in by taking this action. And recall that in stochastic environments, taking the same action from the same state could put you in a different state each time with some other probability. So for each of those states, S prime, we take the probability of ending up in S prime and multiply that by the reward we would get for ending up in S prime plus the discounted value of being in S prime. By doing a summation of this value for all other possible states, we get the value of taking action A from state S, also known as the action value. So that was evaluating a change in the policy at one state to one particular action, but we can extend this to consider changes at all states to all actions, and then to select the action at each state that looks best according to Q pi SA. This is formalized here. The new greedy policy, pi prime of S, takes the action that looks best in the short term after a one-step look ahead according to V pi. And pi prime will always be at least as good as pi, as policy improvement must give a strictly better policy, except for when the original one is already optimal. Once a policy has been improved using V pi to yield V pi prime, once a policy has improved using V pi to yield pi prime, we can then compute V pi prime using policy evaluation again and improve it to yield pi prime prime, and so on and so forth, all the way until the optimal policies and value functions are reached. This method of using policy evaluation and then policy improvement is called policy iteration. The full policy iteration algorithm is shown here, and it's just a back and forth between policy evaluation and policy improvement. So in policy evaluation, V can be initialized to be the state value function for the previous policy, which speeds up convergence. The book defines a simple environment called grid world, in which the agent has 4 possible actions: up, down, left, and right. And actions that would take the agent off the grid leave it in the same state. And the agent moves until it reaches one of the goal states in either the top left or bottom right corners. There is a -1 reward for every step, which punishes long trajectories to the goal and favors shorter ones. Now we can look at an example of grid world in Python code. So this is a Python implementation of that same grid world environment. It's pretty simple. You can use it inside this simple test.py file, and with the render function, you can see what it looks like. So it's a simple 4x4 grid as a matrix, and there's the ones in the corner which represent the goal states, and the agent will start here in the top right, and that's why there's this X here. And then in agents.py, there's implementations of the dynamic programming agents. So there's a couple classes in here. The first class isn't very important. It's just this state class here, and it's used for essentially encoding the environment dynamics of grid world. So yeah, it's not super important. Just know that it's used for calculating the transitions of when the reward should be received when you land on which state. Then there's this dynamic programming agent base class, which just has some base helper functions and things like that. I guess the important class here is this policy iteration agent, which implements that same policy iteration algorithm right here. this policy iterate function. So the first thing that it does is just initializes some state value function and some policy, and then it's going to loop until the policy is stable. And you can see that in the loop, it's just going back and forth between two things, that iterative policy evaluation and then policy improvement. And it goes back and forth with those until the policy is stable, and then it stops. So I guess first, looking at the iterative policy evaluation, it's following that same iterative policy evaluation algorithm. We use some theta as the threshold to determine when we're done. So when the state value function stops changing under theta, then we know that we are essentially done with policy evaluation. So it then loops, and for each state gets the current state value, that's the new state value, and basically looks at all the other states that could be entered. So that's for each S prime. It calculates the probability of ending up in those states and sets the current state value equal to the probability of ending up in that state multiplied by the reward we would get for being in that new state S prime, plus the discount factor gamma times the value of actually being in that state. Then we calculate our delta and make sure if delta is less than theta, it breaks. Other than that, there's the policy improvement function, which similarly follows the policy improvement algorithm that we just saw. So it iterates through all the states, calculates what the current best action is. I'll say the important part of this function is this get action values for state. This is actually implemented in the dynamic programming agent base class, but you can see it here. Basically, it gets the action value for each of the actions from a particular state, and that action value is calculated as that probability of ending up in the next state times the reward you would get for being there, and discount factor, and the value. And then once it has the action values for the next state, it makes the policy greedy with respect to the value function by figuring out which action has the highest action value, and then now it changes the policy to set the action for that policy to be that new action now that is the highest action value. And you can run this agent and see how it performs on the grid world. So you can see here, basically what's printed is both the value functions and what the policy that is that's being learned. I guess all that's important is that after 5 iterations of policy iteration, you can see that it learns pretty accurate value functions for that grid world, and you can see the policy that it learned here as well, which basically will point the agent to entering those terminal states in the top left and bottom right corner. So you can see that yes, it learned successfully. So the main drawback to policy iteration is that it requires a policy evaluation loop at every step, and that's step 2. And that policy evaluation loop in and of itself is an iterative process. So this makes the policy iteration algorithm quite computationally expensive, quite slow. So what if we combined the iterative policy evaluation step, which was step 2, and the policy improvement step, which was step 3, into one step? And we can do this in an algorithm called value iteration. So the algorithm for value iteration is shown here, and you can think of it as similar to policy evaluation in that we're repeatedly updating the state value function v, one state at a time. And each time we update the state values for all the states, we consider that a new version of v. So v0, v1, v2, etc. In regular policy evaluation, we update the value of a state to be a weighted average of the states that could follow, weighted by the likelihood of those states occurring. However, in value iteration, we update the value of a state to be the value of the action that would lead to the maximal expected return, as opposed to a weighted average of the possible next states. So value iteration takes that argmax from policy improvement and directly combines it with the updates for state values. So by doing this, each iteration of the value function gets closer to the optimal value function V star. And we can also see a code example of this. So here you can see the value iteration agent. So it inherits from the dynamic programming agent base class, just like the policy iteration agent. And the important part of it is this value iterate function that just initializes a state value function in a policy, defines that same theta to know when to stop iterating, then loops through all the states. And the important part is really in the calculation of the action values, uses that same get action values for state function that the policy iteration agent uses, that just looks at all the next actions and calculates their action value as the probability of reaching those actions times the reward for ending up in the next states, discounted, and the value of the next state as well. And the important part of the value iteration agent is that it sets the value of any particular state to be the max of the action values of all the actions that it could take. And then the final part is basically just deriving an optimal policy from the state value function, but this doesn't necessarily need to be in the loop. This part could actually be outside the loop. But yes, it just implements the basic value iteration algorithm. And we can test that on that same grid world environment and see how it performs. And what we can see here is after 4 iterations of value iteration, it basically is able to learn the optimal state value functions and the optimal policy as well. And this is in comparison to the policy iteration agent, which took 5 iterations of policy iteration. And remember that each iteration of policy iteration is also longer because it has that iterative policy evaluation step. So just showing how the value iteration was faster and was still able to derive the optimal policy. So now we can compare policy iteration and value iteration. So policy iteration starts with the state value function v and a policy pi, then iteratively evaluates v using the Bellman equation until v is an accurate representation of v pi. So that's that policy evaluation step. Then it improves pi by making it greedy with respect to v. That's that policy improvement step, and this repeats until convergence. And then there's the value iteration algorithm, which starts with the state value function v and iteratively evaluates and improves on v. So it's doing that evaluation and improvement basically at the same time by making the greedy expected updates, or assigning the value of v for any state to be the value of the action, or the max action value. And then just repeats this until convergence, and once done, the optimal policy is trivially derived from v. So a major drawback to the DP algos we've seen so far is that they require a full sweep of the state set, which means looking at all of the next possible states before updating the value of one state. In some environments, for example, backgammon, which has 10 to the 20 states, this can be an infeasible approach. So asynchronous DP algorithms find many different ways to update the value of the current state without looking at all of the next possible states. They could look at only one state before updating the current state value, or they could look at some n number of states before updating the current state value. They could even update the value of some particular states multiple times before the value of other states are updated even once. And the advantages of asynchronous DP algorithms is that they allow DP methods to learn much faster, especially in environments with large state spaces. So avoiding this full sweep of all the other possible states doesn't mean that there's less total computation, but rather that the algorithm doesn't need to get locked into a long sleep before it can make progress on improving the policy. And this flexibility allows asynchronous DP algorithms to progress faster and in a more focused manner, particularly in environments with large state spaces. The term generalized policy iteration is used to describe the interaction between policy evaluation and policy improvement, regardless of the granularity between them. In regular policy iteration, there's a clear separation of these two processes. Policy evaluation finishes for all the states before policy improvement starts. In value iteration, only policy evaluation is completed, or policy evaluation is completed for only one state before it's improved. In asynchronous DP, these methods can be interleaved at an even finer level. So almost all RL methods are described as GPI in the sense that they all have identifiable policies and value functions, with the policies being improved with respect to the value functions and the value functions being driven to accurately represent the policies. And when this whole process stabilizes, a policy is found that is greedy with respect to its own value function. And at this point, the Bellman optimality equations hold and Q star and V star have been found. Two key components of DP methods are that they require a model of the environment and that they bootstrap, which means that they update their estimates based on other estimates. In the next video, we take a look at some other methods that don't bootstrap nor require a complete model of the environment, and we call these methods Monte Carlo methods.